welcome to Two Projects. In this video, we are going to explain the project, a clinical decision support system for heart disease prediction using deep learning. Introduction. Heart disease, a global leading cause of death, is on the rise, with symptoms often subtle until a heart attack occurs. As its prevalence continues to rise worldwide, early detection becomes paramount in mitigating its impact. Identifying heart disease is complicated by symptoms like fatigue and chest pain, often leading to misdiagnosis. Studies indicate that a significant portion of patients experiencing heart attacks or strokes is not identified as at risk using traditional diagnostic methods. The project recognizes the potential of cardiac biomarkers in blood for cost effective heart disease diagnosis. However, their occasional ambiguity necessitates additional tests. The existing risk assessment models reliant on linear relationships may not cover the complexity of individual cases. So, by leveraging machine learning, particularly clinical decision support systems, the project aims to enhance the accuracy of heart disease prediction. By moving beyond traditional methods, CDSS built on knowledge based approaches offer a more sophisticated and precise diagnostic framework. So, the project explores the possibilities offered by deep learning utilizing advanced computational methods. By employing deep neural networks and data imputation techniques, the goal is to develop a robust diagnostic model for heart disease. This approach holds promise for improved accuracy and reliability in disease prediction. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to create a sophisticated clinical decision support system for heart disease prediction by leveraging advanced computational methods, machine learning, and deep neural networks. The goal is to significantly improve diagnostic accuracy. And the goal is to perform an in depth analysis of diverse heart disease datasets to gain insights into factors contributing to heart ailments across different demographics. This step ensures a comprehensive understanding of the disease. And we aim to construct and evaluate a variety of machine learning models, including KNN, linear SVC, decision trees, and deep neural networks with different hidden layers. This aims to identify the most effective models for predicting heart disease. And the aim is to investigate the impact of deep learning, particularly deep neural networks, on enhancing prediction accuracy in comparison to traditional machine learning models. This exploration aims to uncover the potential improvements offered by deep learning techniques. And the objective also includes integrating the developed machine learning models into a practical and user friendly application. This application is designed to provide valuable heart health insights for both healthcare professionals and individuals, facilitating real world use and impact. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front end framework used is Flask, backend framework used is Jupyter Notebook, database used is SQLite 3, and front end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of flow of work. So the first step is important required packages. So in this initial step, essential Python packages such as Pandas, NumPy, sklearn, and TensorFlow Keras are imported. These packages play a crucial role in handling data, implementing machine learning algorithms, and creating deep neural networks for heart disease prediction. The second step is exploring the dataset. So, the exploration phase involves delving into four distinct heart disease datasets: Cleveland, Hungarian, Switzerland, and Long Beach, VA. Understanding the structure and characteristics of each dataset is essential for informed data processing and subsequent model development. The third step is data processing. Here, data processing is executed using Pandas and Keras data frames. Unnecessary columns are dropped, streamlining the datasets for analysis. This ensures that only relevant information is retained for model development and accurate predictions. The next step is visualization using Seaborn and Matplotlib. In this step, Seaborn and Matplotlib are employed for data visualization, offering insights into patterns within the heart disease data. Visualization aids in identifying trends and relationships, providing a visual context for subsequent analytical steps. The next step is label encoding using label encoder. Here, label encoding is applied using the label encoder, transforming categorical data into a format suitable for machine learning models. This prepares the dataset for efficient utilization in training and testing the models. The next step is feature selection. In this step, feature selection techniques are employed to identify and retain the most important variables for model development. This step is crucial for optimizing model accuracy by focusing on relevant input features. The next step is train and test split. Here, the dataset is split into training and testing sets, separating the data for training deep learning models and defining input and target variables for machine learning models. This division ensures the models are trained and evaluated effectively. The next step is training and building the model. Here, a variety of machine learning models, including KNN, linear SVC, Gaussian process, decision tree, Naive, QDA, AdaBoost, bagging, boosting, and deep neural networks with different hidden layers, are trained on each of the four datasets. This extensive training process aims to identify the most effective models for heart disease prediction. And in the next step, as an extension, hybrid models in the form of a voting classifier and stacking classifier are constructed. These models combine predictions from multiple individual models, enhancing overall predictive accuracy and robustness. And the project integrates Flask with SQLite, establishing a framework for user sign up and sign in with secure authentication. This sets the stage for user input and model predictions through a user friendly front end interface. So, after signing in, users are allowed to input feature values relevant to heart disease prediction. The input is pre processed to align with the model requirements, ensuring accurate and meaningful predictions. And the trained models are employed to predict heart disease based on the pre processed input. And the final prediction outcome is then displayed through the front end interface, providing users with valuable insights into their heart health in a comprehensible manner. Now we'll understand about the algorithms used. So the first algorithm built is KNN, that is K nearest neighbors. So KNN operates by classifying a data point based on the majority class of its K nearest neighbors. The algorithm calculates proximity using distance metrics like Euclidean distance. In the context of heart disease prediction, KNN proves effective as it considers the similarity of instances, making it well suited for recognizing patterns within diverse datasets. The second algorithm built is linear SVC, that is linear support vector classifier. So linear SVC aims to find a hyperplane that optimally separates classes in a linearly separable dataset, minimizing misclassifications. This algorithm is particularly relevant to the project as it excels in binary classification tasks and is apt for scenarios with clear class distinctions aligning with the nature of heart disease prediction. The third algorithm built is Gaussian process. So Gaussian process is a non-parametric approach that models the distribution of functions, making it suitable for regression or classification tasks. In the project, this method is valuable for capturing complex relationships in heart disease data without assuming a specific functional form, allowing for nuanced insights. The next algorithm built is decision tree. So decision trees create a tree-like structure by splitting data based on features, facilitating decision making through branches. Their relevance in the project lies in their ability to identify significant features contributing to heart disease, providing interpretable outcomes that aid in understanding the predictive factors. The next algorithm built is naive Bayes. So naive Bayes applies Bayes' theorem assuming independence between features. This simplicity makes it efficient and easy to implement. In heart disease prediction, naive Bayes is effective for classifying instances based on probabilistic dependencies, offering a straightforward yet powerful approach. The next one is QDA, that is quadratic discriminant analysis. So QDA extends naive Bayes by considering covariance between features, accommodating more complex relationships. This proves valuable in the project for capturing nuanced patterns in heart disease data where feature interactions play a crucial role in accurate predictions. The next one is AdaBoost. So AdaBoost combines weak classifiers sequentially, assigning higher weights to misclassified instances. In the context of heart disease prediction, AdaBoost is instrumental in refining prediction accuracy by focusing on instances that were previously misclassified, improving the overall model performance. The next algorithm built is bagging. So bagging builds multiple models using bootstrap samples and aggregates their predictions, reducing overfitting and improving robustness. In heart disease prediction, this approach mitigates variance, providing a more stable and reliable prediction. The next algorithm built is boosting. So boosting builds models sequentially, giving more weight to misclassified instances and emphasizing challenging cases. In the project, boosting proves beneficial for improving model performance in complex heart disease scenarios, enhancing accuracy by addressing difficult to classify instances. And we have built deep neural networks. So deep neural networks, that is DNNs, operate as intricate pattern detectors consisting of interconnected nodes organized into layers. These layers include an input layer for initial data, hidden layers that progressively extract features, and an output layer for final predictions. So the hidden layers varying from 3 to 9 in this project allow the DNN to capture complex data patterns. Each layer improves its grasp on specific features, helping the network spot subtle connections in the heart disease data. The adaptable hidden layers let the DNN fine tune its complexity, making it better at accurately predicting different factors related to heart disease. Now we'll see the comparison graphs of the machine learning algorithms built using Cleveland dataset. So this is the horizontal bar graph comparing accuracies of different machine learning algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis I have F1 scores and on y-axis I have algorithm names. So F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. So these are comparison graphs of deep learning algorithms built using Cleveland dataset. So as I mentioned, the best performing model will be used for predictions. So these are comparison graphs of machine learning algorithms built using Hungarian dataset. These are comparison graphs of deep learning algorithms built using Hungarian dataset. These are comparison graphs of machine learning algorithms built using Switzerland dataset. And these are deep learning algorithms comparison graph built using Switzerland dataset. These are comparison graphs of machine learning algorithms built using Long Beach VA dataset, and these are deep learning algorithms comparison graphs built using Long Beach VA dataset. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So in this folder, I have the Cleveland, Hungarian, Switzerland, and Long Beach VA datasets with class labels on which we will train the machine learning and deep learning models. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are Jupyter source files for each dataset. So these Jupyter source files contain combination of code, graphs and outputs all in one place. So Jupyter source file allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. So now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at default address, local host and port unless configured differently. Now copy the local link provided by the framework, I'm copying it, and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password and click on sign in button. So it has redirected us to the classification page. So now we have to fill in these parameters and click on predict button to get the classifications. So first we'll understand these parameters. So the first one is age. It is the individual's age, a critical factor in assessing cardiovascular risk. The next one is sex, which denotes gender, influencing the prevalence of heart conditions. So CP, that is chest pain type, describes the type of chest pain. Rest BPS is resting blood pressure, which indicates resting blood pressure. The next one is serum cholesterol, which represents blood cholesterol level. And the next one is FBS, that is fasting blood sugar. It reflects fasting blood sugar level. Rest ECG is the resting electrocardiographic results. It indicates results of the resting electrocardiogram. The next one is THALAC, which is the maximum heart rate achieved during exercise. And the next one is EXANG, that is exercise induced angina. It indicates whether angina was induced by exercise. The next one is old peak. It is the ST depression induced by exercise. The next one is slope. It describes the slope of the peak exercise ST segment. And CA is the number of major vessels colored by fluoroscopy. And the last one is THAL, that is thallium stress test results. So now we'll fill in these parameters. So age would be 45, sex is 0, CP would be 2, rest BPS would be 112, cholesterol level would be 0, FBS is 0, rest ECG would be 138, THALAC would be 0, EXANG would be 0, old peak is 2, and slope is 0, CA is 0, and THAL is 0. Now click on predict button. So here we can see the result, that is the patient is not diagnosed with heart disease. So for the given set of parameters, so it has classified it as no heart disease. Now click on home link. We'll try again giving another set of parameters. So age would be 52, sex is 1, CP is 4, rest BPS would be 112, cholesterol would be 230, FBS is 0, rest ECG is 0, THALAC would be 160, EXANG is 0, Old peak is 0, slope is 1, CA is 1, and thal is 0. Now click on predict button. So here we can see the result, that is the patient is diagnosed with heart disease. Click on home link. We'll try again. This time age would be 67. Sex is 1. CP is 3. Test BPS is 152. Cholesterol is 212. FBS is 0. Rest ECG is 2. Thalak is 150. Exang is 0. Old peak is 0.8. Slope is 2. CA is 0. And thal is 2. Now click on predict button. So here we can see the result, that is the patient is diagnosed with heart disease. So similarly, we can give any set of parameters and can get the detections. Now click on sign out link. So the conclusion here is the project merges various machine learning models including traditional and deep neural networks, forming a comprehensive clinical decision support system, that is CDSS, for precise heart disease prediction. Rigorous evaluation highlights successful algorithms such as AdaBoost, decision trees, and deep neural networks, underscoring their significance in improving predictive accuracy for heart disease. Exploring deep neural networks reveals their prowess in uncovering intricate heart disease patterns, enhancing accuracy compared to traditional machine learning methods. And implementation of the CDSs in a practical Flask-based application ensures accessibility, catering to healthcare professionals and individuals seeking personalized insights into heart health. And the project's extension incorporates user testing, authentication, and diverse algorithms, indicating its real-world potential in early heart disease diagnosis and management, contributing to improved patient outcomes.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.